Hello everyone and welcome to this video series, Programming in Java and Python. My name is Hanish and today I'm going to introduce programming through two of the most widely used languages, Java and Python. My goal here is not just to throw definitions at you, but to help you build an intuitive understanding of what programming is, why it matters, and how these languages fit into the real world. I'm coming at this from a software engineering perspective. In industry, programming is not just about writing code that works once. It is about building systems that are maintainable, understandable, reliable, and useful. Java and Python are both excellent languages to learn because they show you two slightly different styles of thinking, while still teaching the same foundational ideas. So as we move through this video, let's try not to think of this as memorizing syntax. Think of it as learning how to communicate instructions to a machine in a precise and structured way. Let's start by looking at what we are actually going to cover in this session. Here are the learning goals for this video. By the end, you should understand why programming matters, what some of the major programming languages are, what Java and Python are at a high level, what an algorithm is, what data types are, and what people mean when they talk about object-oriented programming. I also want to end with the practical piece, because theory without a starting point is just decorative furniture. So we will also look at how to get started with Java and Python using official set of resources. A useful way to think about these topics is that they build on each other. First, we ask why programming exists. Then we talk about languages. Then we move into the logic behind programs through algorithms. After that, we get into the kinds of values programs work with, and finally how larger programs are structured. So before discussing languages or code, let's answer a more basic question. What is a computer program in the first place? A computer program is a set of instructions that a computer executes to perform tasks. That sounds simple, and it is simple in spirit, but it is powerful in consequence. Every app you use, every browser tab you open, every operating system feature you rely on exists because somewhere a program is telling the computer exactly what steps to perform. Programs can range from very simple to extremely complex. A simple program might add two numbers or print a message. A complex program might run a banking platform, a search engine, or a cloud service used by millions of people at the same time. The scale changes, but the essence does not. A program is still a carefully defined set of instructions. This is also why precision matters in programming. Computers are not mind readers. They do exactly what they are told, not what we hope they would understand. That is one of the first mindset shifts people make when learning to code. Once we understand what a program is, the next natural question is, why do we write programs at all? We write programs because they let us automate work, save time, perform calculations, and build systems that people use every day. In practical terms, programming is how we turn repeated logic into something a computer can do consistently and quickly. Think about daily life. Logging into a website, sending a message, booking a ride, streaming a video, checking your bank balance, or analyzing data in a spreadsheet all depend on software. Behind that software are programs handling inputs, making decisions, storing information, and producing outputs. From an engineering point of view, one of the biggest advantages of programming is repeatability. If a task has to be done thousands or millions of times, it is usually better to encode the logic once and let the system execute it. That is how organizations build reliable workflows instead of depending entirely on manual effort. Programming is also how we solve problems at scale. Humans are good at creativity and judgment. Computers are good at following instructions relentlessly. When you combine those properly, very useful systems emerge. Now that we know why programming matters, let's zoom out and look at the language landscape. This slide shows an example language ranking using the PYPL index. The important thing here is not to obsess over exact positions as if we are tracking a horse race with compilers. The bigger point is that some languages consistently stay near the top because they are widely learned, widely used, and supported by large ecosystems. Python, Java, C, C++, JavaScript, and a few others appear frequently in popularity rankings because they solve real problems in industry, education, and research. But popularity indexes are only one lens. They often reflect search interests, tutorials, and learning activity, not a perfect measurement of all real-world software usage. That said, rankings do tell us something useful. If a language stays popular for a long time, it usually means it has a strong practical value, a large community, mature tooling, and many learning resources. That is one reason Java and Python are such good languages to begin with. Let's start with Java, which has been a major industry language for decades. Java is an object-oriented, statically typed programming language that is heavily used in backend services, enterprise systems, financial applications, Androids, and many large-scale business platforms. When people say Java is common in industry, they're not exaggerating. It has been a workhorse language for a very long time. One reason Java became so influential is its platform model. Java code is typically compiled into bytecode that runs on the Java Virtual Machine, or JVM. In simple terms, that means Java programs can run across different systems as long as a compatible JVM is available. That portability was a big deal. Java was originally created at Sun Microsystems and later came under Oracle after Oracle acquired Sun. Historically, that matters because you will often see older Java references tied to Sun, while current official stewardship is associated with Oracle and the broader OpenJDK ecosystem. From a developer experience or perspective, Java is usually more explicit than Python. You write more structure upfront, but in exchange, you often get stronger clarity in large code bases. In professional software engineering, that trade-off can be very valuable when many developers are working in the same system over time. If Java is known for structure and explicitness, Python is known for readability and speed of getting started. Python is a high-level, multi-paradigm programming language that is especially popular because it is readable, flexible, and easy to start using. You can use Python for scripting, automation, backend development, data science, machine learning, scientific computing, and many other tasks. One of Python's biggest strengths is that beginners can start writing useful programs quickly. The syntax is usually less verbose than Java, so you spend less time dealing with boilerplate and more time focusing on the actual idea you are trying to express. That does not mean Python is only for beginners. Quite the opposite. Python is used in serious production systems, research environments, and AI workflows. It is beginner-friendly, but it is not a toy. That is an important distinction. In practice, many engineers end up using both languages at different times. Java might be used for large backend services, while Python might be used for automation, data processing, tooling, or experimentation. So learning both gives you a broader view of programming as a discipline. Now that we have seen two languages, let's move underneath the syntax and talk about the logic that drives all programs: algorithms. So, what is an algorithm? An algorithm is an ordered set of steps for solving a problem or completing a task. That is the core idea. Before code becomes code, there is usually a sequence of logical steps behind it. That sequence is the algorithm. The light switch example on the slide is intentionally simple. Press the button, the light turns on. Release the button, the light turns off. The point is not the complexity of the example. The point is that there is a clear input, a rule, and an outcome. This matters because programming is not just about memorizing language syntax. If you cannot think through the steps of a problem, the code will be shaky no matter which language you use. Strong programmers learn to break problems into smaller ordered actions. As systems grow, algorithms also become more sophisticated. Searching for an item, sorting data, processing user requests, recommending videos, validating login credentials, or routing deliveries all involve algorithms. Some are simple, some are mathematically rich, but they all begin with structured thinking. Once you know the steps of a program, the next question is, what kinds of values are those steps working with? Data types. A data type is a classification of data that tells the program what a value is and how it can be used. This is one of the most foundational ideas in programming because programs do not just perform steps in the abstract, they operate on values. For example, the number 25 and the text 25 in quotes may look similar to a human, but a program treats them differently. One is a numeric value that can participate in arithmetic. The other is text, which is usually combined or displayed rather than added mathematically. So when we talk about data types, we are really talking about rules. What does this value represent? How should it be stored? What operations are valid on it? Those rules help the language and the developer reason correctly about the program. If you skip this concept early on, programming starts to feel mysterious. If you understand it well, many later topics become much easier. Let's make that more concrete by looking at a few common data types you will see in almost every language. Here are some of the most common data types. Integers represent whole numbers. Floating point values represent decimal numbers. Strings represent text. Booleans represent true or false. These categories show up everywhere. If you're storing a person's age, you might use an integer. If you're storing a price, you might use a decimal or a floating point number. If you are storing a name, you use a string. If you are checking whether a user is logged in, you might use a boolean. That is why data types are not just academic vocabulary. They map directly onto the kinds of information software systems deal with all the time. Now, let's look at how Java handles data types specifically, starting with Java's primitive types. Java is statically typed, which means every variable has a declared type. That declared type tells the compiler what kind of value the variable is allowed to store. The primitive data types shown here are Java's built-in basic value types. They include integer types of different sizes, floating point types, a character type, and a Boolean type. These are used constantly in Java programs because they are the fundamental building blocks for working with simple values. It is also worth noting that several integer types exist because programming languages often care about memory size and representation. Beginners do not need to obsess over bit widths on day one, but it is useful to know that these design choices exist for performance, memory efficiency, and interoperability reasons. In most beginner Java code, you will most commonly see int, double, char, and boolean. The others become relevant depending on the use case. Let's look at what these primitive types actually look like in real Java code. These examples show Java's explicit style very clearly. Before each variable name, we declare the type. So we say int age, double price, char grade, and boolean is ready. This is one of the clearest differences between Java and Python. In Java, the language wants a type information upfront. That helps the compiler catch certain mistakes earlier and makes the intent of the code more explicit. The note here about wrapper classes is also useful. Primitive types themselves are not objects, but Java provides wrapper classes like integer, double, and boolean when object behavior is needed. That becomes important later when using collections or frameworks that expect objects. For a beginner, the main takeaway is simple. Java likes explicit structure, and that structure is part of why Java scales well in large code bases. Not all Java types are primitive though. Many important values in Java are actually reference types. Reference types are different from primitive types because they refer to objects rather than storing simple built-in values directly. In Java, strings, arrays, classes, interface, enums, and collections all fall into this broader reference type world. Why does this matter? Because real software systems rarely work only with tiny isolated values. They work with structured data, domain models, collection of records, configuration objects, user requests, and many other object-based concepts. So if primitive types are the atoms, reference types are where you start building molecules and systems. That is where the design side of programming becomes more visible. Let's look at a couple of small examples of Java reference types. In this example, string name stores text, and the array number stores multiple integer values. Both are reference types in Java. This is a useful moment to notice that programming is not only about storing one value at a time. Very often, we need to store collections, sequences, or grouped information. Arrays are one way to do that, and Java collections such as list, map, and set build on the same general need. Once you move into application development, reference types become central. You represent users, products, orders, requests, responses, and many other concepts using object-oriented structures rather than only primitive values. Now let's switch gears and see how Python approaches its built-in data types. Python is dynamically typed, which means you generally do not declare the type of a variable explicitly when assigning a value. Instead, Python determines the type at runtime. The built-in data types listed here cover many common categories: integers, floats, complex numbers, booleans, strings, lists, sets, dictionaries, bytes, and none-type. A lot of everyday Python programming revolves around these built-in structures. One of Python's strengths is that these types are easy to start using immediately. You do not have to write much setup code to work with them. That is one reason Python is popular in education scripting and exploratory work. But easier syntax does not mean no discipline is required. Dynamic typing can speed you up, but it also means you need to be thoughtful about what values your program is working with and how these values are used. Let's make that concrete with some Python examples. These examples show Python style nicely. We simply assign values such as age equals 25, price equals $19.99, name equals a string, is ready equals true, nums equals a list, and a person equals a dictionary. Notice what is missing compared to Java. We're not declaring int, float, or string explicitly in front of the variable names. Python infers those types from the values provided. This is one reason beginners often find Python more approachable. The syntax gets out of the way quickly. You can experiment, test ideas, and build small programs with very little ceremony. At the same time, understanding what the actual types are is still crucial. Python is dynamically typed, not magically typeless. The rules still exist. They are just applied differently. So far, we have looked at values and logic. Now let's look at one of the most common ways larger programs are organized: object-oriented programming. Object-oriented programming, or OOP, is a way of organizing code by modeling parts of a program as objects. An object combines data about something with behavior that something can perform. This idea becomes useful when programs grow beyond a few small functions. Instead of scattering variables and logic everywhere, OOP helps you group related information and actions together in a more structured way. For example, if you are building a banking system, you might represent an account as an object. That account can contain data such as balance and account number, and behaviors such as deposit, withdraw, and transfer. That is much more intuitive than having unrelated variables and functions floating around in a giant procedural soup. In professional code bases, OOP is not the only style used, but it is extremely common because it helps model real entities and maintain structure over time. To make the idea more intuitive, let's use a simple everyday example: a car. Think of a car. A car has data such as color, speed, and brand. It also has behavior such as starting, accelerating, and braking. That combination is exactly why it makes it a good example for OOP. In object-oriented programming, we represent that with a class. A class is like a blueprint. An object is an actual instance created from that blueprint. So a car class might define what data and behaviors a car has, while my car could be one specific object built from that class. This is a powerful concept because it lets us model software in a way that feels closer to how we think about real systems. Once you understand classes and objects, many application designs begin to make more sense. Now that we have covered the core concepts, let's move to the practical question most beginners care about: how do I actually get started? Getting started, for Python, the easiest official starting point is the Python downloads page. If you're completely new, you can also follow the Python beginner resources. If you want a very beginner-friendly coding experience, Jupyter Notebook or Jupyter Lab is a great option because it lets you write and run code in small sections instead of managing full project structure right away. That interactive style is especially helpful when you're learning syntax, testing ideas, or explaining code step by step. It is one of the reasons Python is often introduced through notebooks in education and data-focused work. For Java, the key point is to install a JDK, which stands for Java Development Kit, that gives you the tools needed to compile and run Java programs. After that, you can choose an editor or IDE such as VS Code, IntelliJ IDEA, or Eclipse, depending on your preference. The main idea here is not to overcomplicate setup. Use official sources, get a working environment, and start writing tiny programs first. Beginners often lose momentum by trying to build a spaceship before learning how to tighten a bolt. At this stage in the presentation, I would simply reinforce one message: use official installation pages where possible, keep the setup minimal, and avoid drowning in tool choices before you have written your first few programs. If you're choosing between starting with Java or Python, Python usually offers the gentler path into programming syntax and experimentation, especially with Jupyter. Java, on the other hand, gives you early exposure to explicit types, structure, and the kind of organization commonly used in larger software systems. So there is no wrong choice here. The best first step is the one that gets you actually coding consistently. I've also pasted these links in the description of this video. By now, you should understand the basic idea behind programming and some of the major components involved in learning how to code. We will cover more topics in the upcoming videos. And if you like this video and would like to watch more, Subscribe my YouTube channel, The Dignified Professor, and stay tuned for the next video.